Okay, well, thanks all for being here. Um, so I'm trying to find, what you want to hear from me, and I discussed with a few people, and some people are interested in understanding better data science. Some people are interested in knowing more about scikit-learn. Some people already know scikit-learn. Who uses scikit-learn here? Okay, not many. So this is not a scikit-learn tutorial. I'm sorry. What I'll be talking to you about is a bit how we work as data scientists. I'm a researcher. I look at applications of data science, so that I guess that makes me a data scientist. But also a bit how we work to build scikit-learn, and a bit also what's in scikit-learn. So a bit of all three. This does have a bit of what I'll be talking about has a bit of a Python bias because I've been doing too much Python for the last many years. So really the scope of data science, I was trying to think how can we define it. And it's really how we can get insights from data, whether it's to move to productions or to inform policy. So inform policy in a company would be business intelligence. If I'm interested in public health, because I'm interested in public health, then that would be informing public health policies. And if you want to look at the past, for instance, there is an interesting application of data, even though it was not was not really data science back then, is a study in the Lancet in '98 that showed a link between autism and vaccines. Now, this study was forged. It's well known now that this study was forged. This was incredibly dishonest. As far as I'm concerned, Andrew Wakefield should be in prison. And the consequence is, across the years, that there's a drop in vaccination, and that these days we have measles outbreaks in Europe or in the US. So that's an example of the consequence of data. I think we can do better than this. And to just give you a tiny idea of what I do in my team, for instance, is interested in basically in brain imaging, and we've been doing things like linking autism to brain connectivity. That's just a quick idea of what you can do with data. So first, I'd like to discuss a bit how a data scientist works, for the better or the worse, and what kind of constraints it puts on the workflow. Just in case you're interested in either in becoming a data scientist or in managing data scientists. Then I'll talk a bit about how to, I'd like to say, not work like a data scientist, and basically how to think in terms of library design. And that's the kind of things that we have in mind for scikit-learn. And then I'll do a short introduction and short discussion about scikit-learn and machine learning in Python. So I'll start with iterative thinking, how we work as data scientists. And if our goal is to get insights, and that's overall what a data scientist does, our work is going to be based on intuition and experimentation. So in a sense, it's a different work than the standard developer. Who of you is a developer? Who of you is not a developer? Who doesn't like to raise their hands? Okay, so if you're pretty much, most of you are developers. In a sense, a data scientist tends to define himself as someone different from a developer, because there's this whole idea that we're going to build some intuition by interacting with the data, and it's fairly important. And we don't, start with a well-known problem set. So really, we work by conjectures and experiments, and we keep looping. So it's really an iterative work. Now, the danger is that we shouldn't stop there. And I would say that too many data scientists stop there. We should consolidate what we do while keeping flexibility. And this consolidation should be more of a software one, but also more of a statistical one. We want to control our conclusions. So yes, some people claim that data science is not coding because it's based on intuitions and iterations. And some people claim that it should be held to different standards than software. I disagree. I think we need standards because whatever we're going to do, whether it's put in production or informs policies, has consequences. So in research, what I do, but also in companies, often data science teams don't have the reputation of providing extremely good software because they don't see themselves as software developers. And one of the problems is that it's not very reproducible, and this is relevant because it's just the way people work, and we need to reproduce conclusions if we want to trust them. So if we look at why things are not reproducible, if we look at how a data scientist works, well, the problem is that there might be steps that are missing, and that's related to the interactivity. We might have libraries that change. That's a fairly standard problem of software in general. We might have non-portable code, standard problem. We might have statistical instabilities or numerical instabilities. That's maybe a bit different in real life. No one knows where the information is and the data is. That's very common. So we've got a mix of technical and human problems. And I guess my conclusions on this is that code quality does matter and that manual steps are evil. Even though when you work to develop intuitions, manual steps are necessary. So I like to separate the way I work in data science, and this might not be surprising if you all have a developer background, but I think some of the ideas of developers can be adapted to data science, though they do need to be adapted. So typically, we sometimes talk about model view controller, separation, and in a sense, it's partly feasible in data science, where the model would be the statistical model, the business logic of what we're trying to analyze. The view would be the visualization, and the controller would be how we test our hypothesis. The reason I'm pointing this out is that it's not at all obvious in the data science code. This idea that we need to separate the statistical models from their representations and from how we test hypotheses with them is not very present in the code that people write. So I based on this, I think that it's really important that the code that we write has imperative APIs, and actually fairly simple imperative APIs, as simple as possible. So we don't want to describe an analysis with a JSON file that specifies the questions that we want to ask. Neither do we want to describe it with a full object-oriented framework. We want to describe it with an API that can easily be assembled to ask different questions. And then I personally separate my work in 3 different kind of scripts. Some of them are focused to ask questions, some of them that are focused to model the data, and third are focused to process and do figures. I version control everything, of course. I try to control the data. That's maybe the hardest part of data science is if I can't control the data, if I have modifications in my data, then I will have modifications in my conclusions, unsurprising. And I need to know whether the modification in the conclusion is because I did something different with my code, I upgraded a library somewhere, or the data changed. So if you're working with small data, versioning your data is easy. If you're working with very large data, versioning your data is very hard. So you might want to consider checkpointing databases or version databases, even though that's a real challenge. So the goals of this separation is, of course, to decouple steps, to reuse code. It's actually really hard, if you're not careful in what to do, to reuse codes between multiple data analysis. And the reason is that unlike a typical development question, it's an open-ended question. It's not, you don't have a clearly set goals. So how do I personally work? That's based on many years of experience of doing research, so open-ended questions. I always start with a script. By a script, I really mean a script. There's not even, if name equals main. And I'm just playing around with the question I'm interested in. And I just want to get the thing done as dirty as possible, as quick as possible. As I work, I identify blocks that are meaningful by themselves, and I move them to a function. I love functions because they define, a local scope that is constraining, so that's a problem, but it requires me to identify input and output variables. And if you don't do this, you don't realize how constraining it is, because when you're playing around with your data, you're basically modifying everything. So the minute you move something in a function, you've got a cost that you're restricted. So this is actually good because it allows you to make this a reusable unit. Maybe I'm preaching to the choir if you're all developers, but it's not obvious when you're doing data science. And so the way I get over, I can keep having intuitions about what's going on inside my function is that I use interactive debugging. If there's something I don't understand about my function, and that's something that happens all the time, I will need to go inside it and understand what's going on with the data. So the reason why we have those problems, by the way, in data science, is that we don't always control the data that comes in our functions. So we get really weird things sometimes. So this is why I need to go back and basically open up the black box and figure out what's going in. So I extremely heavily use interactive debugging. I could not work without interactive debugging. But functions are my basic reusable abstractions. As my functions stabilize, I move them to a module, a small library that I am going to reuse. And I use those modules to share between experiments. I may run all kinds of different experiments, and I want to reuse the code. In the enabled testing. So once again, maybe I'm preaching to the choir. Maybe 100% of you are testing all your code, but that's seldom the case in data science. Why is testing crucial? Above all, it's crucial because it gives you confidence that you can modify what you're doing without breaking everything. That's the most important thing. Once you've done this, you're able to refactor your analysis. So we're not talking about production code here. We're talking about analysis code. You can still refactor it because you can check that your refactoring gives the same result. So that avoids you basically having legacy analysis code that you're stuck with for years. And of course, something that is crucial is that I need to delete code and files. And that is also a challenge because if you're doing recommendations for business or public policy, you don't want to delete things that you've done in the past because you might need to go back to them. However, I claim it's crucial to do this because it's the only way you avoid drowning under information. I see too many projects with hundreds of analysis code and no one knows where the information is. So that's why we have version control, okay? So basically, version control is the tool I use to avoid drowning under information, which requires using it well. So in practice, this is harder than it looks. And one of the reasons is that each iteration step, remember, I'm working in an iterative way, each iteration step might actually induce a fairly long compute time. I have large data sets and I need to crunch them. So if I want to check that what I'm doing is still correct, I may have a day or a few days of computation. So as a consequence, I become scary of changing things because I can change a small thing and then I don't know the consequence it has had. I have no magic bullet for this. The only thing I can tell is that I use my tools, so my editor, my version control as much as I can. The closest we have to a magic bullet for this is memorization. What I call memorization is if I run a function twice on the same data, it should give, if it's the same function, it should give the same result, hopefully. So it's basically, so we wrote this small library, joblib in Python that basically stores, so computes a hash of the data that comes in and stores the results that comes out. And we use it extremely heavily to be able to keep, those quick iterations, even if there might be long-running computations. So the trick here, compared to many other memorization library, is that we need fast hashing, well, reasonably fast hashing of the input data. And so this is a Python implementation that works on fairly large data sets. So the reason why this is extremely useful is that we can just always continue our quick experimentation, but without writing a full framework to test on different versions of the data. So I guess the conclusion of this part is that we want to be using software engineering best practices. And if you're software engineers, it might sound obvious, but it's not, because there's a fairly big mismatch between the quick iterations of data science and the interactive work of data science and the best practices of software engineering. So the way I personally work is that I have what I call the ladder of code quality, which is I have a set of different steps that are all with an increasing cost. And I adopt them one after the other, especially when I come in a new project. The first thing is that I want to use a good editor and a good linter in it. PyFlakes, for instance, but any kind of good linter. Second thing is coding conventions and good naming. This is pretty much costless. Having good names does not cost you anything. Version control, once again, if you're developers, you probably all use version control, but not all data scientists do this. So if you're in a team with data scientists, you probably need to train them to do this. And remember, version control, when you don't know it, is scary. So if you're with people from a different culture, you need to bridge to this culture. Code review, once again, preaching to the choir, but code review is great. And this will force a data science team to write code that is more easy to audit. Unit testing, now that's a more challenging one. Not all code in data science is easy to unit test. And that might be where sometimes you need to stop. It might be a good thing not to do unit testing on a data science project. And that's a call you need to do. Depending on the specific aspect of the project, you might want to unit tests or not some parts. And if you're going to go all the way, then you're going to make a package with control dependencies and building, if you have build, and ship it to production. And so we've gone from insight, mucking around with data, to production. And that's a process. Something that is really important here is that we have increasing cost as we go down the line. And because of increasing costs, we need to apply those practices at the right moment of a project. So we shouldn't do premature software engineering. It's very costly. And the trade-off we're in is the one between over versus under engineering. If our goals are only to generate insights and not to push to production, then we need to stop early in that ladder, maybe before testing. And it's quite important to start as fast as possible and to experiment, above all, on the data to get new ideas, basically. And as we get new ideas, we will consolidate. If we require, for instance, unit testing from day one, we will spend a lot of time on bad ideas. I know this now. Maybe I'm giving a message that is not a common message for developers. As a developer, because I'm also a developer, I will not admit any code without tests. Okay, so once we've done all this, we have a library. And now I want to shift a bit to discussing library design and maybe discussing the things that we've learned doing scikit-learn. And I like to say that if doing research is like crossing oceans, doing software is like building bridges, and you can build bridges wrong, as you can see here. So why is it interesting to think about building libraries in the context of data science? Because I think those libraries should be a bit different than the libraries that you have in web or in other settings. And one of the things, for instance, that I'll claim is that functions are better than classes. And the reason is that they're more easily reusable in a context that they were not made for. So if you get classes, I'm not opposed to classes. If you know scikit-learn, we have many classes. But classes come usually in with a specific logic, whereas function, they have an input and an output. They're really easy. Over the years, I've grown to value a lot shallow objects, what I call shallow objects, which are basically understandable via their surface, a small number of attributes or methods, which define, of course, an interface. And I don't want there to be many, and one of the reasons is I want my library to be usable by a non-expert. So a data scientist, for instance, who's not comfortable with object-oriented programming, or you, if you don't know data science. I want you to be able to pick up my library and really easily use it. And I claim you can, by the way. Another important point is that all my data should be in universal data objects. So don't create specific data structures for input and output. So these are going to be NumPy arrays, pandas data frame, dictionaries, things that everybody know. So then, of course, we need to define a good vision. We need to define a problem that we want to solve. So we can't solve all the common problems. So 3D plotting and statistics, for instance, in the same library. Basically, we need to define a product when we're doing a library, and we need to test it. Testing a data science code is very challenging. So in scikit-learn, what we do, the vision of scikit-learn, is that we provide you atomic tools to build data science pipelines. And these are statistical tools, and we want to test that they're statistically correct. So we're basically going to test their mathematical properties. So now this gets a bit in the details of the mathematical properties, so it means that we need to understand those mathematical properties. And this is what we test. And something that we've learned over time is that our tests should run fast. If our test suite takes 3 hours to run, it's going never to be run. We do have continuous integration, but still. And so something that we've learned through this is that we should be able to make everything absolutely reproducible. And there's a lot of random number generation, for instance, in a statistical code. Which means that we need to control the random number generator perfectly in all our code. So that's an interesting exercise that taught us a lot. Finally, something that we do in scikit-learn that works really well is that we have a contract with the user on the API. So all our objects have an interface. They take data in. You can apply a method to data, and you can query the object in a certain way. And we have black box tests that basically test that all our objects can take all kind of different data in. If they don't accept this kind of data, they should raise a meaningful error. They should never crash. They should always give reproducible results. So we call these common tests, and we run them on all our objects. And that's really been extremely helpful to increase the quality of our code base because all our objects behave similarly. And of course, each time somebody reports a bug, we add a test. That's classic. So now I'd like to talk a bit about scikit-learn and about machine learning, basically. And maybe I should define machine learning. Machine learning is about building predictive models. So models that can predict something about new data. So first, what tool stack do I use? I only work in Python, and it's been like this for 10, almost 15 years. Why did we choose Python? Because it's a general purpose language, because it's not a numerical language. I want to be able to bridge to people who don't do numerics. Because it's interactive, and because it's easy to read and write. And it's about crossing the boundaries between fields. You're mostly developers, but it may be interesting to work on a project with a medical doctor. And I've worked on a project with medical doctors, and we can teach them Python. It's not that hard. And I think there's a lot of value, because often the value of data science is about bridging different fields and bridging people with more of a software or computer science background with people from an application background. So our basic data structure in Python is the NumPy array. It's basically building on the scientific Python stack. And you can think of a NumPy array as a float star. So basically a pointer to an array of float. That's not much more than this. It's got metadata that goes with it, which means the type, the structure, But it's actually a very simple structure. It's quite easy to understand the memory layout of an NumPy array. And this is why it's universal across all kinds of libraries and applications, and it can easily be shared across languages. Now, this becomes extremely important because maybe you will have to share your data to other environments, maybe Spark, for instance, maybe C code. With an NumPy array, it's quite feasible. You're basically handing the pointer around. Now, when we have Spark, we're talking to the Java virtual machine, so Java virtual machine doesn't like pointers, so it copies the data, but that's their problem, not ours. And now NumPy arrays can connect to other libraries, such as pandas. So pandas is, you can think of it either as a database in memory, or you can think of it as Excel, programmable Excel, depending on your background. We can connect to scikit-image, so it's about processing images. We can connect to SciPy. SciPy is basic scientific Python code, so all kind of core numerical routines. Now, machine learning. As I said, machine learning is about making predictions from data. For instance, you want to learn to distinguish apples from oranges. So you're given examples, or samples, we call them. You're given examples of what you want to learn. So here are apples and oranges. And you want to distinguish the one from the other, and you want to learn this from the data. The challenge is to generalize. If I learned that apples were green and oranges were orange, I will fail on the new data. That's the difficulty. Prediction is difficult, especially about the future. So the challenge is to learn as much from the data, but not too much. If we've learned too much from the data, we don't generalize. Here's another example. I want to fit data. They're my data points. Which of the two models do you prefer? Who prefers this one? Who prefers this one? Maybe you should prefer this one. It fits the data better, doesn't it? I mean, there's less error. It's interesting. The human mind is not fooled. The human mind tends to prefer this one. But this one fits the data better. I guarantee you, there is less distance between the line and the data points. So why do you prefer this one? It's more simple. And that's crucial. It's back to what I was telling you. You need to fit the data as well as possible, but not too well. You need to learn as much as you can from the data, but not too much. And so the intuition is that this will generalize better than this. Here I've shown you new data points drawn from the same distribution. And now on those new data points, the error is smaller here than here. But on the points that you had already seen, the error was smaller here than here. So there's this notion of the difference between what we call trained data and test data. Test data is the new data that's going to come, and we want to generalize to the test data. And the challenge is exactly this, because your test data is not exactly the same thing as your trained data. And there's going to be statistical difference between the two. And so the idea is that we're going to learn a model that's as complex as possible and as simple as needed for a certain notion of simplicity. And that is going to be application dependent, even though some notions of simplicity are more general than others. So here, I've shown you a family of models. It's actually a continuous family of models as parameterized by a certain smoothness. And the challenge of machine learning is going to find the right family of model and to find the right model in this set of trade-offs. So for instance, this could be the age of the captain as a function of the size of the boat. And you could try to learn a predictor that goes from size of the boat to age of the captain. This is basically what machine learning does. I mean, it's hidden in a library that takes data in and does things and gets predictions out. But it's always the same concepts, and it's just statistics. Any questions on this, by the way? Any intuitions? Any? Nope? Okay, so scikit-learn. Our goal in scikit-learn is that you should be able to do machine learning, but without having to be an expert. Now, you can use it as an expert. That's possible. But our goal is that you can start easily with it, and then you can learn, and you can carry as far as you want. That's really important for us. You don't have to understand what I've shown before to use scikit-learn. It's better if you do. You'll use it better. So it's a library. It's not a program because we want to be reused as much as possible because we want to be flexible. It's an imperative API. You need to write lines of code in Python, but it's much easier to include in an ecosystem. So we want you to use it to do things that we haven't thought about, and people are doing this every day. It's easy. This is real code that will really learn a predictive model. You import some magic thing that's called here an SVM, support vector machine. It's an algorithm. You instantiate it, and I'm going to call this a classifier because it learns to classify, aka to give classes, so apples, oranges. And then I will fit it on data, and I've got two NumPy arrays here, one that describes what I'm trying to predict, and I call it y, and one that describes what I'm going to try to predict from. Okay? So here, this may be features of apples and oranges, like color, size, and here this may be labels, apples and oranges. Okay? And now I predict, and when I predict, I give only the features, and the output is whether it's apple or oranges. Now, there's one challenge there, is that we're taking pretty much only numerical features in. It's not quite true, but mostly. So it means that you need to convert your problem to numerical features. And that's actually what's difficult. And this we don't do for you because that's domain specific. So depending on your domain, you will have to get numerical features that describe your problem set. And labels, we call these labels, things to predict. And then you can use scikit-learn. This might be counting statistics of users. This might be measurements that you can do. This might be counting words. So if you work on text, you will be counting words. We even have an object to count words to easily transform. Actually, it's the next slide. Any questions on that? No? Yeah. The number one challenge is to get to this problem where I have numerical data and labels to predict. Once you have this, you've pretty much solved the first iteration of your problem. So that's what I was saying. The input data is really a 2D numerical array. And if, for instance, you have text documents, they could be queries in a web form. What we're going to do basically is that we're going to count the number of times each word occurs. And now that's a numerical matrix, and now I can do machine learning on this. So once you're there, you've solved your first problem, and maybe that just generated a second one, is that now you need to deal with a lot of data. So how can we be efficient with very large data? And there are basically two problems that you can think of. One is I have a huge number of observations that are described by not many features. That's the typical situation in web, let's say. I'm counting, I'm observing behavior of users, and observing many users, but I didn't observe much of their behavior. Now, if I do medical applications, I will have a small number of individuals. Luckily, there are not that many people who go to the hospital with a given pathology. However, I might have images of their brain. So it's another problem. Most likely you're interested in this one, and this is what's being known under the name of big data, even though it's completely misleading, because those two problems actually are big in terms of terabytes. So in this setting, when I have many data points, what I can do is, I can't even load these data points in the memory. They're too big. So what I can do is I can do what's known as an online algorithm. The idea of an online algorithm is that it processes the data chunks by chunks. So it's basically chunking. And scikit-learn has a bunch of them. The reason I'm telling you this is that what you're going to do is that the first thing you're going to do is you're going to try with a toy problem, and it's going to work. And then you're going to say, yippee, I want to apply this on my full data set. And depending on the situation, you might be in this regime. And actually, if you are, you're lucky because it means you have a lot of value because you have a lot of data. If you're not, don't worry. Most of the problems are not in this situation. Most of the problems fit in memory. I think I'm simply going to skip this part because you're most likely not in these situations. If you do medical imaging, you need to reduce your number of features, but you're most likely not in this situation. So a few things that are, I was hoping to have more scikit-learn users, so I was hoping to announce exciting things that happened recently in scikit-learn. I still will, but given you're not using scikit-learn. So this happened a few years ago. This is the most used model. It's the logistic regression. The logistic regression is the simplest model that you can think of to make binary decisions or multi-class decisions. And it's the one you should, it's one of those that you should try by default. And now it has a solver that's known as SAG or SAGA, and that works very well if your data fits in the memory. It's really turnkey, load the data in memory, give it to logistic regression, it works really well. Now this is recent, this is in the 021 release, which just came out a few weeks ago, and it's gradient boosted trees. So we already had some, but they're much faster. So gradient boosted trees, I guess those two models, linear regression and gradient boosted trees, are the two models that are most likely to be useful for you. If you had a huge amount of data that are things like counting statistics or age of people of different nature, which a lot of web marketing problems have, then gradient boosting is probably the tool that will work well for you. And it used to be that other libraries, other open source libraries such as XGBoost were much faster than us. So we fixed the problem and we're now as fast as them. So you don't have to use other libraries, you can just use us. Maybe that's an anecdote because that's more for advanced user, but maybe it's interesting to see this. So we now have what's known as metric learning classifiers. So the idea being, I'm always telling you, you need numerical descriptions of your data, and that can be challenging to have. So for instance, you're looking at offers, for instance, selling apartments. And you want to describe them by numbers so that when you've described them by numbers, two apartments that are close, have numbers that are close, are apartments that are more likely to interest the same people. Okay? If you're able to do this, if you're able to find a numerical representation of those houses or flats, you haven't fully solved your problem, but you've really helped the problem a lot. And so in the latest version, we have what's known as a large margin nearest neighbor. And what it really does is it finds a representation of your data, and it can be a low-dimensional representation guided by labels. So if you have labels about the data that you know, if you've got classes on your data, it will project the data so that classes, the same classes are closer, okay? So here my classes are green, blue, and red, and I've done a data projection so that same classes are closer and different classes are as different as possible, as distant as possible. And so when I consult in companies, this is actually quite useful. So something that we've been working on lately is to use distributed infrastructure. So between us, I consider that distributed infrastructure is a pain. The way I personally work is we have a few big computers in the to 500 terabytes of RAM. No, 500 terabytes of RAM. No, 500 gigabytes of RAM. 500 terabytes of disk, and we work on them. We're super productive. We don't have to bother about distributed computing. However, it's not very elastic. You need to buy these things. And second is that if you're in a corporate infrastructure, the infrastructure is already there, and it might be useful to use it. So we've been working on plugging onto corporate infrastructures, whether it's Hadoop or other kind of distributed computing. And the way we do this is that we use the parallel computing that's embedded in JobLib, which is a library that we depend on, and we're working on plugging it to different distribution engines or different storage engine. And so we can do parallel computing on a single computer, and you can set backends. But what you can do these days, and it's not as robust as it should, but it's improving, is that you can use a library that's called Dask to distribute the computation across multiple computers. And Dask actually has many backends, so Dask can reuse just about any distribution infrastructure that you might have. So the combination of scikit-learn, JobLib, and Dask allows you to address distributed computing. This, I should say, is a fairly challenging work because we need to persist the models, persist the data, move it around. So it's a bit a long-running effort. So we're used on a regular basis by 500,000 people. We're open source. We don't make money out of this, and sustainability is a bit of a challenge for us. And it's a common problem in open source. Basically, open source these days is infrastructure. And for this reason, we've created a foundation. And so these are our partners. And I need to stress that it's a sponsorship for a foundation. They're not getting anything out of it. They're not even, they're giving recommendations, but they're not even choosing which features go in and which do not. So we're very grateful to them. So it's time to wrap up. I've talked a lot about code, but some problems are better solved by documentation than code. I really strongly believe in this. And so for this, we've also been working on basically a book that is an introduction to scientific computing in Python. It's an online book. There's no print. And it's, reading it and doing all the exercises and everything is like maybe 10 to 20 hours of work, so a lot. But you can read it chapter by chapter if you're interested. Have a look. And there's a chapter on scikit-learn, by the way. And it's really based on code examples. So to wrap up, I've discussed code for data science, and it's really about experimentation. And I think if you can take something away from this talk, is experimentation is crucial and just progressive iteration. I've discussed about code quality for data science, and I've shown you scikit-learn. And go ahead, have a look at the website. Thank you.
Thank you very much, Gaël. So, who has a question? Anyone? More like a project question. Like, how many people are involved on the Scikit project?
Scikit-learn. There are other Scikits.
Sorry.
On Scikit-learn, we have something like between 10 and 20 core developers. We have more than 1,000 people who contributed the line of code to Scikit-learn. And in terms of people who are paid on it full time, we do have people paid on it full time. And there are 4 in my team and 2 in New York. And then we've got half times in Australia and in China.
Okay, cool. That sounds very international. And is there what's the roadmap ahead? Like, what are you planning for the next, 1 to 2 years?
I really want distributed computing to work better. We also have technical details like the better gradient boosting because it's crucial for many companies, banks and insurances, for instance. And interpretability, so opening up the black box is something that comes up as very important. Also, model persistence and quality checking, so that you can put something in production, and then really make sure that this thing stays stable.
Okay, that sounds cool. Thank you very much, Gaël. Big round of applause. We actually have a question, so stay on stage. Nico, here you go.
Hello, can you
Hi.
hear me?
Yes.
Hey, I have a question because we talk a lot about ethics in AI and how it can be used to evil purposes, right? So is there a code of ethics for using scikit or anything like that?
All right, I'm with geeks, so I can. Okay, scikit-learn is open source.
Yes.
One of the tenets of open source is you can't control how people use it, and that's basically part of the open source initiative definition of open source. I do not think that scikit-learn is any different from any technological tool. It can be used for good or bad. Now, we could discuss about the ethics of tech as an environment. And I think, as a community, and I feel part of the tech community, we need to think about what we do with our tools. And we've not always been good about this. But I don't think it's it's not specific to AI. In tech, we say things like, go fast and break things. We think that disrupting is a good thing. We say things like, fake it until you can make it. To me, all these things are wrong.
Thank you.
There's another question.
Hi, thank you very much. I have a question about education, actually, as you're quite involved in teaching. I get a lot of data science candidates that haven't learned anything at school about software craftsmanship.
Me neither.
So I was wondering, have you heard or are you involved in any plans for the future to teach a bit more about quality software to students?
I don't teach a lot, but quality. So there are two things where we need education. One is on software good practices, and the other one is on data science. For software good practices, it does take a bit of time, but software carpentry is an amazing set of tools. They're online, of courses. They're online. There are workshops that are organized all the time, and they're geared towards non-coders. So it's really, really great way of learning. People can either go to a workshop or use the online tools. We will probably be doing a MOOC on scikit-learn, even though I'm afraid by the workload that this entails. But we won't be covering code quality. It's going to be software carpentry for code quality.
Awesome. Gaël, thank you very much. Big applause.